my brain right now.
Okay, great. Luvar and Habex, I think.
Luvar, Habex, Lynx, Origins. There's a bunch. And then
so all four are moving forward.
They're in there. It's like I said.
Here, do you think the Unistellar is a good kind of daily driver, or is it time to then get a like a Rasa? Like I really enjoyed using the Rasa.
Yeah, definitely. Yeah, if you can
I mean the
something
Rasa. I mean,
that large.
Because I mean, just the pier makes it so that it makes your mount life and your polar alignment life that much easier.
Yeah, something like this, I'm envisioning like a remote observatory where you wouldn't even be able to stand in it. It would just be a box to weather protect the telescope, and it just sits out there.
Yeah. And we need to weather protect. I mean, the rain here is just ludicrous.
Yeah,
It's just been crazy, just day after day after day of 50 millimeters a day of rain.
I tell you
It's
though,
just
when you have an
awful.
observatory, you observe so much more, because when it's just the sky's clear, you unlock, slide the roof back, turn the scope on.
Yep.
You don't have to polar align, you don't have to lug, you don't have to drive. It's like I observed so much more when I had an observatory.
Yeah, absolutely. And that's the goal, is probably get in the rainy season, I'll probably get maybe 4 or 5 nights a month of observing, but in the summer season, almost every night is clear skies.
Yeah.
So so I think the thing I want to do is sort of bring back the virtual star party, but this time have an observatory under my control that's just right there, that I can go and control the telescope and then just be able to have that be the background of the thing, because it was great working with OPT. And they bent over backwards to give us access to this amazing observatory, but still there was just so many things beyond their control, and it was in the middle of the desert in California, and someone would have to drive out and fix it, and you just couldn't depend on it in
I remember,
when
I was doing them from Florida, it's always a matter of coordinating who has clear skies and who doesn't.
So anyway, that's my that's the plan. I think is we'll finish the studio, and then in the
finish
spring,
the house first.
Well, the house, the house comes, like, we're gonna live in the studio while we build the house, so we're probably not gonna break ground on the house until 23, I think.
Wow.
So we're gonna live in the studio for probably 2 years plus. We're sort of spending all our money to build we've got a nice road, and we've got hydro, we've got electricity, we've got a septic field, we've got a well. So, and once the studio is done, we'll be kind of out of money. So then we'll have to wait a couple of years to take a crack at building a house. But the studio is kind of house-ish. Like, it's designed to be livable for a couple of years.
Yeah.
Okay, the keyboard is. Oh yeah, we can definitely hear Pamela's keyboard, but I don't think the audience can hear Pamela's keyboard.
Probably not.
Yeah. Okay. All right. Well, let's get this thing started, since we're all here ready to go. Okay. Hello and welcome to the Weekly Space Hangout for Wednesday, November 3rd, 2021. Happy birthday, Chloe. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about proposed Centaur mission to catch a comet in the active formation, what's coming for the big Decadal survey announcement. Researchers think they know exactly where the Mars meteorites came from on Mars, and a bunch of updates on the Mars rovers, and maybe some other stuff, depending if we run out of time. Joining me this week, we've got, this part, like, it's obvious, like, just joining me this week, read the screen. Joining me this week, we got Dave Dickinson. Hey, Dave.
Hey, my first show of the season, turns out.
So that's a unistellar behind you again.
Yeah, I have. This is our new Equinox telescope. The other one is my Orion 5-inch, just for comparison. But I reviewed the Equinox telescope for unistellar. I've been bringing out the star parties and playing around with it. Completely smartphone controlled. It's a neat little toy.
How long do you get to hang on to it for?
Till they ask for it back. I kind of hope they forgot, but it's a neat toy to I bring it up here on the roof in the apartment. And what really amazes me with it is I can do deep sky imaging from downtown Norfolk, which usually I wouldn't even bother to go after, like a lot of the fainter targets, like M51 and things like that. You wouldn't even see at the eyepiece, but this will do deep sky imaging from urban areas, which is kind of cool.
Yeah. I mean, we know those telescopes are going to take over the world. It's just a matter of time. Like, they are the future.
They got to get the price down a little bit, I think.
But they're too expensive. Yeah.
Well, the first CD players were $500 too, and the price went down on those.
Yeah.
I think eventually they can get these under $1,000. I think they would be a big mass market.
Yeah. All right, and we've also got Dr. Nick Castle. Hey, Nick.
Hey, how are you?
Good. Welcome back again to this.
Thank you.
as a regular co-host. This is turning into a regular thing. So what have you been up to?
I've been working on grant proposals like a crazy person.
Right.
It's amazing how much free labor there is in the education market.
Yeah, it's like you're either working on grant proposals or attempting to do the science. You never get a chance to take a break. Like when you're working
Not
on the
really.
science, you're also thinking about the next grant proposals. And then when you're working on the
Absolutely.
grant proposals, you really should be working on the science that you did before. Yeah. Yeah.
Because every
Well,
3 years, you got to win at least one, or you're out of a job.
no pressure.
It's nothing like sciencing for your supper.
Yeah, exactly. All right. So before we get into this week's special guest, which, like, spoiler alert, he's on the screen. But anyway, before we get into this week's special guest, I just want to give a huge thank you to our good friends at the Weekly Space Hangout crew. They are our fans, really our producers, and they sort of hang out and talk about space and astronomy and all the cool stories that are going on. And so if you want an amazing community to join in enthusiasm about space and astronomy, this is the place to go. And I mention this every week, and maybe people don't think I'm serious, but I'm deadly serious. I am so lazy that I perfectly happy to hand off all responsibility of choosing guests, bringing them on the show, to all of the great, amazing people at the Weekly Space Hangout crew. So if there's like some special guest that you want to bring onto the show, all you have to do is just invite them. And then as an executive producer of the show, they can't resist. They have to show up. And that's the kind of power and authority you get in the space community by being a member of the Weekly Space Hangout crew. So go to wshcrew.space and you can sign up, and they'll give you all the information that you need. All right, let's get into this week's guest. We've got Dr. Adam Dipert. Adam, welcome to the Weekly Space Hangout.
Thank you so much for having me. I'm really excited to have a conversation with y'all.
So, all right. So the question I always ask people is, who are you? What do you do?
I have been a circus performer for the past 20 years. And after I started that right after high school. And then I started going to colleges, which I got super addicted to until I ended up with a PhD. And now I do experimental nuclear physics, and I study things about the nucleus of helium-3 atoms and neutrons.
So what would be, say, the title of a recent paper that you worked on?
Well, I just published a paper this year called Choreographic Techniques for Human Bodies and Weightlessness, which kind of references the topic we're going to be talking about.
That has nothing to do with helium atoms.
Yeah. But yeah, I had a paper last year that was about a high voltage in superfluid helium system. They're all kind of complicated, long names that I don't remember. Yeah.
I guess all I really want to know is how long till nuclear fusion? Is it 30 years away?
That's not really the thing that I'm working on. I'm more in. So we are studying something called the neutron electric dipole moment, and this, in the context that of space enthusiasts, I'd imagine you believe in a Big Bang, and there's a lot of reasons to believe in a Big Bang. But one of the reasons not to believe in a Big Bang is that there's not equal amounts of matter and antimatter in the universe, and if that had occurred, then we would see that. And so there's some difference between how matter and antimatter progress through time. And if we get an answer to our research, then that might give us a clue as to how the universe ended up in the way that we view it now.
So, I mean, we'll get to the juggling in a second, but so place your bets then. What do you feel is the answer? What is the evidence leading you towards as a possible explanation for why there's more matter than antimatter in the universe?
So I feel like a really good scientist in the sense that I truly don't care. I am not worried about what it is. I'm having a great time studying it. And I think, it's kind of like the classic CERN situation. Like, if we find it, that'll be cool. If we don't find it, that'll be interesting.
Right.
Right. And so it's like, either way, it's a win-win situation as long as your curiosity remains stimulated. So yeah, I think there's some evidence that antimatter might evolve differently than matter. But who knows? And I get to be on the front lines of kind of picking it apart right now. And yeah, it's really fun to just do experiments and study it genuinely.
it is. It's such a fascinating concept, and it's one of the great mysteries in astronomy. If you asked astronomers what are the top 5 mysteries out there, that would be on pretty much everybody's list. Is why do we have this discrepancy between matter and antimatter? So it's a fascinating conversation, and it's great to see that it hasn't been solved yet. Like, we get to watch this being figured out in real time, back and forth.
Yeah, and our experiment has been evolving for 15 years, and even we're not going to take data till the last part of this decade probably, and this question is 2040, 2050 until we're going to have something to believe in.
Yeah, but hopefully in our lifetimes.
That would be cool.
What instruments are you using to take the data? What telescopes?
Oh, so we are putting helium-3 and neutrons into a superfluid volume, and then we monitor the interactions between them as they spin around, and we apply a strong electric field so that we can observe if the neutron might have some displacement between its quarks. And so it's really like super low temperature physics in a laboratory that we're doing in order to investigate this. And its link to astrophysical phenomenon is really through like quantum field theory and some pretty deep, math topics. And so, yeah.
All right, well, let's move on to the juggling portion then. As we do in every guest, we talk about the science, and then we also talk about their ability to juggle. So you call yourself the Space Juggler?
Yep, that's what I've been working with lately. So I've been on 3 parabolic flights so far, and before I went on my first one, I wrote a computer program to simulate the human body so I could understand how it could rotate, because rotations are really weird and super complicated, and definitely a big question when you think about approaching an asteroid. Like, how is it rotating? Because they're very complicated things that can be happening. And as I was studying that, I discovered that if a person is in a standing position and they spin, or if they're in a standing position and they want to spin in the most stable way, they could spin like a cartwheel, around their belly so that their head spins in a circle. But I realized I hadn't seen any astronauts doing that. And so I wondered, like, why am I not seeing people doing this? And it just kind of stuck in my mind. And as I thought about it, I realized that's also the only way you can spin and keep facing the same direction, because every other way you're constantly facing a new direction. And then I was thinking about how balls travel in straight lines when you're in weightlessness. And I wondered, okay, if I'm spinning in a circle and balls are traveling in straight lines, I could throw them down into the circle, and then I'd spin around and catch them on the other side. And so that's where it started, was just like, when you think about space juggling, most people think about like throwing to another person or bouncing it off a wall or whatever. And kind of that sequence of ideas came into, maybe a real idea, a real concept. And so here in this image that's being shown, this was one of my first models. And it's a person standing, and the blue axis is the maximum moment of inertia axis, and so that's the most stable way they can spin. And then the red axis is the minimum axis, so that's another stable rotation. But all of the other ways that you would spin, you would end up kind of flopping around, or pretty complicated things happen. And so yeah, it was like started with this computer model and then turned into a whole couple of years of exploration now.
So I'm sort of imagining this in my mind. So you're throwing, you're spinning like a cartwheel in space, and you're throwing the ball down and essentially catching it on the other side as you have rotated around.
Yes.
And so you have to get both your speed of turning as well as aiming the ball, and you've got these kind of like almost Coriolis effect going on, right?
Oh, that not kind of like.
Kind of. You do have a Coriolis effect. Yeah.
I was going to say,
why don't you roll that video?
There must be a video of you doing this.
Oh, yeah.
Yeah.
Yeah, can you play that video, Pam? Yeah, so it's pretty neat because the Coriolis effect and the centrifugal force both influence the trajectories of the balls when you're viewing it in the rotating reference frame.
Oh, cool.
And I wasn't actually expecting the rotating reference frame when I started. It was only after I built the apparatus so that I could view myself from the big front that I thought, I wonder if I spin the camera with me while I'm spinning, like what would that look like? Because I found in my head, I'm always trying to map out space and imagine, where the balls are in space. And in my head, I was always thinking about them as trying to be in straight lines, even though I'm spinning. And once I saw the video, I started saying, oh, no, the spinning is real. And so here the video has stopped and you can see the balls traveling in straight lines. And
that's cool.
And so it was really a surprise to be like, oh, wow, what are these trajectories? And how is it that I can anticipate the type of behavior they're going to have?
And I mean, you mentioned earlier, you've had a chance to do 3 parabolic flights. That does not seem like a lot of time to practice in the real environment. You get like what? You get like a few 15 seconds, 20,
like
15,
20 seconds. Yeah.
20 to 30.
Okay, 20 to 30 of weightless each time until you vomit.
Yeah. They actually don't stop the plane just because somebody vomited.
Yeah. Carry on.
Yeah. That and
add that to the show, I guess.
That was one of the challenges because, so I'm a professional performer, and so I really value practice before I go out, and I'm kind of like in the moment and needing to satisfy my conditions. And so I wanted to figure out how I could just practice ahead of time. And that's why I built the apparatus originally, was just to like get some experience so that then when I went into weightlessness, I would be able to do it a little bit more quickly. And here you can see my really awesome spacesuit that we made. I'm really proud of our spacesuit. And so at this moment, since I have filmed it in the apparatus and not on a parabolic flight, I'm actually kind of happier that I did it this way and that I really followed through with the practice regime, because I could never have learned to juggle for 5 minutes if I had done it only on parabolic flights. And if you think about trying to just do all of your practice in a parabolic flight, then there's no way you could figure this stuff out in that amount of time. And actually, if you want to roll that last video again that you were playing that had the rotating and non-rotating frame, I think there's some cool things that I could show in there. So here you see on the left a ball moving in a straight line. And then on the right, you can see that same trajectory, but viewed in the rotating frame. And so you can see when it goes through the middle, it kind of makes that teardrop shape. And this is a slightly altered trajectory, and it kind of makes that bigger shape. And so these are like throws either from the same hand to the same hand or from the leading hand to the lagging hand. You can get this type of really cool rotation in there where it goes back over and crosses itself.
It's like a spirograph.
Yeah. And then these are a bunch of throws to different positions on the circle, right? Which depend on how far you rotate before you actually do the catch. And so it's neat because in Earth juggling, you are always working with a parabola. But in this case, it really looks like you get the opportunity to work with different types of shapes. And I have done all the math to work it out and understand what these shapes are. And they're all types of roulettes, which other shapes like hypotrochoids and trochoids and spirographs and stuff like that, they're all roulettes as well. And I just really am happy that I found kind of like a general set of equations that show all of these trajectories in a single equation. And now you're kind of seeing what it looks like, in video with the camera rotating and not rotating. And I think it's just really profound to see and understand the differences between things when you just change your perspective.
Yeah, that's really neat. And so obviously the goal will be to do this for real in space for Inspiration 5 or whatever is the next flight. Have you figured out a way to do a more dramatic test or even teach an astronaut or something?
Yes.
So what's the plan? What do you mean, yes. I listed a bunch of ideas there.
Yeah, of course, I would love to have the opportunity to actually go and do this. I think Dear Moon would, of course, be my favorite version of having this opportunity, because then I would have a lot of days in a row to do different types of artistic projects. Because this is not the only form of object manipulation I've been envisioning for weightlessness. And yeah, I am talking with some astronauts, and I think it's very realistic that we will see space juggling on a space station near you very soon.
That's cool. I mean, they're nerds.
They're very much nerds.
And this is the kind of thing, like, you spend any time talking with an astronaut, and some of them are, test pilot daredevils, but most of them are nerds. And you sit down and start to talk to them about cameras or astronomy or anything. And yeah, I'm sure almost every astronaut you talk to would be all over this and wants to give that a shot. Is them finding the time to be able to do this and their busy schedule. How much time would NASA let them have out of their busy schedule?
Yeah. Yeah, and that's one aspect of it that I think is really I'm really excited about, is just like letting it go. This is like a movement technology that
Right.
it'll be really exciting to see anyone else adopt it and go explore it, and to have just to have a cool opportunity to contribute to what movement and weightlessness will be like. It's just been really cool. Yeah.
I got an interesting question from a viewer a while back, where people want to know, like, what would sports be like on, say, the moon or on Mars or just in space itself? So based on what you've experienced so far, what do you think, if there was, we're 100 years in the future and there's sports in space, what do you think it might be like?
So, we, of course, usually when people talk about this, they imagine arenas that are basically three-dimensional extensions of a two-dimensional surface, and then maybe they put the goal in the middle of each end or whatever. I think it's going to get a lot more complicated than that, because it's more interesting when you think about, the athletes would need to have the same skill set that Olympic gymnasts do, or high divers do, or something like that. The ability to do self rotations where
Mhm.
you are floating and you're not touching anything, and then you extend your arms and move them, and now you're like facing in a new direction. Those are elements that I haven't seen the space sports enthusiasts talking about, is like not just what the game is, but what are the technical skills that you need to have to achieve competent movement. And so what another aspect of space juggling that I really wasn't expecting was that once you go into this rotating frame, those are actually the exact same trajectories that we'll be seeing in rotating spaceships. So
Mhm.
if you throw a ball in a rotating spaceship, then it will do one of those patterns that I showed. And I found a pretty huge gap in the literature, because when people deal with these things mathematically, they always do it where they think about the ball moving in a line, or the object, and then they apply a rotation. But if you're living in a rotating spaceship, you need an equation which represents it in your reference frame, in the rotating frame. And so it's been pretty cool to really embody that, and try to figure out, like, what does it look like while you're spinning, not when you're
Mhm.
stepping back, just watching somebody spin. And so the funny, I get asked about space sports often, and I guess my answer is, I'm really excited to go see people put their bodies in it, and then we'll get our answers. And that it's
Yeah.
really hard from this position to have any real ability to anticipate.
Well, I mean, and I think that, these trajectories that you're showing, like, if you are an astronaut on board some kind of rotating space station, that's the trajectory of your head. That, this difference that you're experiencing from your feet to your head, this is going to be very disorienting, and is going to feel like you're always sort of walking upstream, as you're, depending on which direction you're going. If
Yeah,
you're
exactly.
moving spinward or anti-spinward, or whether you're moving inward or outward, it's going to have a different feeling. You're going to be leaning to one side, and these all of this motion that you're showing is, but imagine it's your head. You're experiencing these. And I think that people underestimate just how disorienting just living on one of these rotating habitats is going to be, unless they're gigantic, kilometers across. It's
Even
gonna
the
be,
kilometer length ones still
yeah.
have different gravitational effects than we do on Earth. You know, if you're on a kilometer radius spaceship with a 1g force right at the edge, and you just hold a ball and you drop it, it will still fall 10 centimeters off to the side.
Yeah.
Right. That's relevant. and yeah, it's also
If you're
something
pouring
that
water,
even exactly pouring water.
Yeah,
Yeah,
yeah.
yeah. And it's something though that you can acclimate to, or I found that I've been able to acclimate to. When I started, I was able to spin for about 5 minutes before I got down out of my apparatus and then stumbled and fell up against the wall. And, it was just like,
Yeah.
like, whoa. And
Yeah.
then I sat until 10 or 15 minutes. And I was
Yeah.
just like, I have to do this, even though I was still dizzy. And now I can spin for more than 30 minutes. Hop out, my thing's kind of high, so I have to like climb down a ladder to get out of it, and I come out of it not dizzy at all, just like balancing like a cat, ready to go. And so it really I think it'll be interesting to see how much and how often that type of acclimation is common, right? The people at the Ashton Grable Spatial Orientation Laboratory at Brandeis University have the big rotating room, and they found that when you first put somebody in there and you have them reach forward to grab something, of course, their hand shoots off to the side, right? And within 2 minutes, they can consistently reach forward and grab that thing and have become acclimated to the Coriolis and centrifugal force experience. And they can get it up to like 35 RPM. So, they can get a pretty decent tilt in the resultant vector. So, I'm excited. I can't wait to see it.
Yeah, I mean, even like so far, everything's just been so rudimentary. Like, you've got the space station, and people are on board, and they're floating around in microgravity. But as we start having potentially larger spaces, rotation, people are going to have to learn an entirely new way of just getting around and being in an environment. It's really fascinating, and it's exciting. I'd love to try it. Like, it would just be the best to be in that environment and starting to experience just a completely different way of getting around. You're kind of flying if you want to, but also you're sort of drunk walking around on the outside. Yeah, it's gonna be neat. I like it.
Yeah.
So when place your bets. When do we see that first astronaut juggle?
I'm betting within the next year.
Awesome. All right. Well, we're going to keep an eye out for that. Now, you're going to stick around for the rest of the show with us, but I want to give you a chance to sort of shamelessly self-promote your work. So if people want to see what you're doing, where should they go to follow you?
Yeah, so I am the Space Juggler on my website and on Instagram, the YouTube. Yeah, I'm
On
that
the
old.
YouTubes?
Instagram, Facebook, and I am going to be releasing a theatrical short of space juggling, so a short film next week, and then I'll be releasing a behind-the-scenes film the week after, and then I'll be releasing a film about the math, and so, yeah, if you are excited about this, following on any of those would be really great. And if you really want to participate and to be up to date and to know when videos are being released, I have an email sign up on my website, and it is I'm not going to spam you. I totally will only send you short notifications about space juggling.
Sounds good. All right. Well, Adam, stick around. We're going to move on with the rest of our stories, but definitely feel free to jump in, and I may tag you as well to provide some insight. All right. Dave, you're on my screen next in line. Which story do you want to talk about first?
Let's do the Centaurs first.
Okay.
Yeah, this is an interesting study out of the University of Chicago, and they were looking at sending a mission. This is a really long-term mission, which I think is kind of interesting that we're looking this far out, to study a Centaur asteroid. Centaurs are these asteroids out beyond Saturn and Neptune. They're kind of we know they're kind of transitional objects. We probably haven't seen one up close before. And I say probably because there's an idea that some of Saturn's moons, I noticed in research like Hyperion, might be captured Centaurs. So Cassini and Voyager missions might have we might have had a preview of kind of what one of these objects are up close. But this mission would go out to Jupiter's orbit. And what the key thing we want to do, and I know that slide's kind of busy, but it's from the study. It actually shows the transition region where Centaurs, we know that these objects get captured. They only have a lifespan as Centaurs coming in from the Oort cloud further out of a few million years, which isn't really that long in terms of the solar system. So we know they're getting replenished from the Oort cloud, and then they're transitioning to Jupiter family short period comets, short period comet being with an orbit of less than 200 years in the inner solar system. Jupiter does this goaltending job. I know we like to talk about there's some aspects of Jupiter like deflecting, but I think it also sends things into the inner solar system too. So
absolutely does. Yeah.
It's a goaltender, and it also is deflecting in, and you can see that with these transitional objects that are going Centaurs into short period comets. Now, what this interceptor would do is, and I think this is an interesting idea, that you're seeing more ideas for mission. There's ESA, the European Space Agency, has another idea for a mission called Comet Interceptor. And this would sit out by one of the Lagrange points, the L2 Sun-Earth Lagrange point, I believe, in Earth orbit as opposed to Jupiter orbit. And what they want to do, objects like Oumuamua, when it comes by, it was moving so fast, and we all saw it only when it was on its outbound leg. There was no way to chase it down. What you really need is something sitting out there without a mission, really, for objects of opportunity. And that's what European Space Agency's Comet Interceptor would want to do. If something came in that had, it would have to have the right parameters, be passing near the right point in the ecliptic. But they think within 6 years or so, they could have a target. Well, you got all these large survey telescopes, Vera Rubin and everything else that are coming online. We're expecting to see more of these interstellar objects. But with a Centaur mission would be kind of similar in that it would sit out at Jupiter's orbit without a target, although there is one potential target that they would like to get to by 2063. I don't know if I'm going to be around in 2063 to report on it or not, but called P2019 LD2 Atlas. There is an object that they think is going to have a close passage in 2063 near Jupiter. And this would be a target for this kind of mission to a Centaur to potentially sit out there and catch this thing in the act of, there's a Hubble image I put up there of it on the slide that it's already starting to act comet-like. So we would see one of these Jupiter family comets for the first time. Yeah, it's already out there past Jupiter, but it's starting to exhibit some cometary activity for a Centaur anyway.
Right. But as I understand, though, it's similar to the asteroid or the interstellar interceptor mission that ESA's planning, that it would go out into the area and then wait for an interesting target. Yeah,
it's a target of opportunity, which I think there is some precedent. You think about New Horizons. I mean, it knew it was going to Pluto, but past that, Arrokoth wasn't even discovered yet at that time. So, and even now, New Horizons, they're looking for potential. Alan Stern was hinting at here in the next year or so, we may know about a potential third target.
Oh, I hadn't heard that.
It's just something that they're looking. It still has some fuel, so it has to be roughly along New Horizons trajectory. But I think it's interesting that we're repurposing missions for more targets of opportunity like that out there. I mean, it's out there. We might as well get all the science we can out of it. So.
Yeah, and so I mean, like, imagine a mission like that. It loiters around in the Centaur region, finds a target of opportunity, aligns its orbit, and then really gets to watch this Centaur come online, make this transition from just a cold, icy nothing to the first time a comet has become active. And we've never seen a comet at that stage of its activity. They've always been a lot more mature.
And Lucy is kind of going out to the same regime, out to Jupiter's. It's going to the Trojan asteroids that just launched. So there's some precedent for that. Lucy's kind of interesting. I didn't get to talk about it last time, but I researched it and wrote about it. And it's going to a lot of targets. We're going to get a lot of science out of it. And the orbit of it alone is really fascinating it's actually was closer to Jupiter when it launched than it will ever be when it's out at the Trojan Lagrange points. So.
Right. That's funny.
Yeah.
Yeah, the Trojan regions are pretty big. That's really cool. I'm looking forward to this mission.
So
Yeah.
we'll see if we make it to 2063. But I think it's interesting that they're
Right.
even looking at missions that far out. And like I
Well,
said,
but like it doesn't have to be 2063. There could be some other object. Like they could launch it. It could wait and find something sooner.
For this, in like I was saying with Vera Rubin and all these other survey scopes coming online, they may find some other. Now, this one PD2 Atlas target is the only one that they know is transitioning. But it's like with Oumuamua, there are probably some that we're missing right now that are coming through the inner solar system.
Yeah.
That
awesome.
You really need something there ready to go to chase after it.
Very cool. All right, Nick, let's talk about the source of the Martian meteorites. Let me guess. Mars.
Funny you should mention that. Yes, Martian meteorites are from Mars, but there's been a long-standing debate over exactly where from Mars are these things. Now, to be clear, this newly published paper isn't saying all Martian meteorites are from one crater. But one of the things that we can figure out is when a lot of Martian meteorites were ejected from Mars. There's a way that we can do back the math on isotopic ages to figure out an ejection age. Basically, it's when these things were scooped out of the ground, started being exposed to solar radiation, and that starts the clock on some of the short-lived radioisotope chronometers. So you can pull that back and see that there's a large group of somewhat compositionally similar, and I use somewhat very loosely, meteorites that all have about the same ejection age. So there's been this thought that they may have come from the same impact crater. Now, it takes an impact crater something like 300 kilometers in diameter to get enough energy to kick stuff off of the surface. You're not talking like big, deeply excavated things coming out, because that would all be destroyed. You're talking about stuff that was, say, near the surface, gets hit, and then just kicked, bounced out. And so the question is, this has been approached a number of times in the past, trying to argue, all right, compositionally, these things look like they're coming from the big volcanic regions, usually either Tharsis or Elysium, which are the two regions outlined in white in this paper from the this figure from the paper. Yeah, going well today. There have been other arguments that tried to say, let's look at the spectroscopy of the surface and match that to spectroscopy of meteorites to limit the class of which ones are plausible to be craters that could have lifted any particular group. This study took a totally different approach and said we can get much better age information if we look at secondary craters off of primary craters. Now, secondary craters are 2 to 5% of the size of the primary. So for a 300-kilometer impact crater, you're talking about something that's just a few kilometers. That's getting pretty small.
Yeah, to go interplanetary.
Yeah. Well, you're not actually looking at that as the source for the meteorites. You're looking at that as your information for how old was the source crater for those secondaries. Secondary craters also have a different shape. They're a little shallower than the primary impact. So we can tell them apart from primary impacts. They also are short-lived on Mars. That is, the dust tends to come by and fill them up, or they tend to get eroded away. So they've got a pretty short lifespan. So if you see a crater with a fair number of those around, you know it's young. And if you really know the pattern of those things being around, you can figure out about how young to a level that you can start to narrow it down to say, okay, which of these really big craters is actually at that 1.1 million year ejection age that we need for these meteorites. Now, what's exciting here is this is the first time we've narrowed down the list from maybe a dozen or so to saying it has to be one of these two, and we're pretty sure it's this one, not that one. So it's a really cool approach. It actually required quite a bit of machine learning algorithm development, an application to very large data sets. And it's an exciting result because one of the big problems with meteorites is we don't have a field context. It's kind of like saying, I have this basaltic rock from Earth. Okay, where? Is it from Hawaii? Is it from the Aleutian Islands? Is it from Iceland? Because those are three wildly different places to get a basaltic rock from. And it tells you very different things about the inside of the Earth, which is the goal in studying what comes out of the Earth.
in my mind, those meteorites had been floating around in space for hundreds of millions, if not billions of years from when that impact had happened. But you're saying
Yeah.
that they're much more recent, that
Yes.
that the Earth is scooping them up fairly quickly after they're ejected from Mars. There's not a lot of old debris still kicking around in the solar system. It's either been kicked out, gobbled up by a planet, thrown into the sun, and so
Yep.
it's just the most recent stuff that's finding its way from planet to planet.
Yeah, so meteorites that have a long residence time in space, basically what happens for that is they fell down onto an asteroid and found a home on that asteroid for a long chunk of time until that asteroid got perturbed, probably nailed by something else, but now at higher velocity so that pieces went flying off. If it's just free floating in space, a smallish rock, meaning several meters, has a residence time of something on the order of 20 million years as being kind of that's a long time floating in space.
So, like, I mean, I'm sort of imagining you're like taking all of these crater count information, you're feeding this into a computer, it's it's searching through just all this data to find the right crater that matches. Do you think we could get to a point where they'll all be mapped out and we'll know roughly how old they all are, where any meteorite that gets found, you could pretty quickly then look back at this database and say, oh, it came from here, and then
I
start
would
to
absolutely love it if we got to that
start
point.
to piece together. It's like you could piece together the geography of Mars from Earth by looking at the shrapnel.
It would be incredibly cool to be able to do that. Now remember, it's still going to be a very biased sampling because there's only so many really big craters on Mars. So you're only getting pieces from so many locations. And there's a lot of blank space in between, but there's no way we've got chunks of. But if we can figure out where each of our collections of different types of Martian meteorites are coming from, I should mention, by the way, this is a particular suite of what we call geochemically depleted, almost entirely olivine ferric shergottites. That's for the specialists listening in. But these are shergottites are things that kind of look like a basalt. That is, the inside of the planet melted, these things came out. Olivine ferric is a particular type. There's several types, olivine ferric, poikilotic, and basaltic, which just talk about what minerals are in it. And then there's different geochemical reservoirs. So this is one specific subgrouping in that they're identifying. But if we could do that for a lot of these different sets, then we could start to say, hey, which ones are actually related to one another? Like, can we convert one type into another? Which volcanoes are erupting what sorts of magma? And what's that tell us about what's going on inside of the planet there? Because whatever's been driving Tharsis has been making huge volcanoes for billions and billions of years. We don't have anything like that on Earth. So what's that do to the chemistry of what comes out? And what's that tell us about the inside, that it can be erupting for billions and billions of years? Like, basically, you'd think the water tank of magma would run out at some point.
Well, I mean, we learned from InSight that there are still fairly significant quakes happening on Mars. There still is some magma gurgling around. So it doesn't seem impossible that you could even to this day have a fissure open up and a little bit of magma pop out. So I guess
I live in hope. I'd love to see hope.
Yeah, I know. It's funny. I ask planetary scientists about this, and like, is Mars dead? And they're like, probably, but we're not sure. Like, there could still be, like, it could be that there was active volcanism on, say, Olympus Mons as recent as 5 million years ago. So
the estimates vary. I've been asking the same question since I was a little kid. You know, there are volcanoes on Mars. Have they erupted in my lifetime?
Yeah.
And the answer is not that we're aware of. So if so, really small. But could they erupt? That's an outstanding question that we frankly don't have an answer for yet. We think probably not.
So all we need to do, so I'm just sort of thinking, like, instead of sending a sample return mission, couldn't we just smash a lot of big asteroids into Mars, throw a pile of debris up, wait for it to make its way to Earth, and then just have it rain down and just send us samples? feels
despite it being a horribly complex series of missions required to bring a sample back from Mars,
yeah.
I'd really rather go that route.
All right. Well, we'll shelve my evil, scientist plan. All right, Dave, let's talk about the Decadal survey.
Tomorrow is the day. The big Decadal survey, Astro 2020, comes out, and it's been delayed a little bit, but it seems like it will be worth the wait. And we're kind of looking to see what telescopes. What are the big winners? This is more than just even the space telescopes and ground telescopes. This is the overall direction that the marching orders for astronomers for the next decade, as far as what they're going to be going after. So, and it's up in the air. Like you think about things like James Webb that are just getting ready to launch. We were talking about before the show. That was almost we're thinking now 2 decadal surveys ago,
right,
that was like a proposal where they were saying that this was going to be, and we're just barely launching it now. So a lot of the big scopes that are up right now are, of course, LUVOIR is the major one. There's a full scale LUVOIR that's a 15 meter, I believe, and there was a downscaled LUVOIR that's like an 8 meter mirror that would fly out there. This would be ultraviolet optical infrared. That's where the bulky acronym comes from.
Hubble, the true Hubble successor.
This would be the true Hubble successor. James JWST isn't quite. It's actually more of an infrared. Infrared doesn't really sell telescopes as well. So although it's important, and you have to do infrared in space. One of the ones that's up is an infrared workhorse, is Origins. And another one, Lynx, would be the largest. That would be a successor to Chandra. That would be the largest X-ray observatory ever put up. And the fourth one that's in running is HabEx. HabEx, I think, is kind of interesting. It's smaller. It's a 4 meter mirror, but it would have a coronagraph. It's looking for habitable exoplanets, is where the acronym comes from. But it would have a star shade, free flying coronagraph. A lot of these, in order to actually image and spot Earth-like exoplanets and things. So it's interesting to see if what flagship missions are going to go ahead, if they're going to do all, some, or none, if it's a combination, if it's another direction. There's the questions about things like the Sophia Observatory that's been off and on again on the chopping block, if that's going to continue going. There's the Giant Magellan Telescope and the 30-meter telescope, part of the ELT program, where they're going to be going with that. I mean, this is all as we're looking at Vera Rubin's coming online. Nancy Grace Roman is going to be launching the WFIRST. If you look back with James Webb and WFIRST, Nancy Grace Roman, and those instruments, there was a big... it took a while to get them to the launch pad, and James Webb very nearly didn't happen. Nancy Grace Roman very nearly. I think it's interesting that was one of the spy satellite mirrors that the National Reconnaissance Office gifted to NASA, and it was still hard to get. It just shows that even if you give NASA a telescope, they gave them 2, and they haven't had any real plans for what they're going to do with the second mirror. So just because you have the mirror doesn't mean it's easy to get the telescope into space. And
the timeline on these is like what, 2035?
We'll probably be looking at the 2030s, 2035, and there's ideas now that LIGO is up with advanced LIGO. We'll probably be hearing about with gravitational wave astronomy and a lot of this multi-messenger astronomy and what kind of upgrades they might be wanting to do with that. I think gravitational wave astronomy is interesting because it's not even on the electromagnetic spectrum. It's literally giving us another regime to look at, called multi-messenger astronomy. So I think that might be a big deal as well.
And I mean, there's a bunch of really interesting ideas that are starting to come up as well. Things like a radio telescope on the far side of the moon.
We don't have Arecibo anymore. So and we have to stay competitive. China is the leader in that market now with the fast 500 meter radio telescope. There's things,
and I think they're building the largest steerable one as well.
Oh, I haven't heard that.
Yeah, they're building a giant steerable radio telescope as well. So they're cornering the radio market for sure.
Thinking of radio, like the Very Large Array, that's very old. There may well be like a next generation Very Large Array idea out there. This is all speculation, but tomorrow we should find out exactly what direction they're going to be going with all
Awesome.
this stuff. It's going to
Adam?
be interesting.
You've been listening quietly. Which one are you most excited by of the 4 follow-on observatories?
Well, I really love LIGO. That's,
So
but
none of the above, but LIGO. Yeah.
yeah. Well, I think, like you said, gravitational waves giving us an entirely different way to look at the universe. That's like, whatever 2 years ago was the first time we had more than one type of data on any event in space.
Yeah.
That's really cool.
In the 2030s, European Space Agency's LISA gravitational wave interferometer should be flying. They did their proof of concept a couple of years ago. So
things like LISA can, for example, utterly resolve the crisis in cosmology. Like having a proper gravitational wave observatory capable of detecting various mergers. You're getting essentially a raw calculation of the distance to all of these events, and you no longer have to worry about apparent brightness. So many big problems in this go away.
To do a free flying detector in space, you have a huge baseline where LIGO has these 2 interferometer arms that are only a couple kilometers long. So, a huge baseline, you're going to see a lot
I think they're going to be like 10,000 kilometers as the baselines for LISA. Yeah. But anyway, we're totally tangenting. Before we're running out of time, Nick, give us some quick updates on Perseverance before we close out the show and whatever else is happening on Mars.
Well, Curiosity and Perseverance are both chugging along. An interesting thing happened recently with Perseverance. One of the frustrating things about dealing with a rover remotely is that it tends to move extremely slowly compared to what a field geologist would be able to do in a day. A day where you moved 80 meters was a huge drive. It takes a lot of planning to push for that. Perseverance just did a drive that was something on the order of 168 meters in one go. And part of what's remarkable about this is they only had about the first 20 meters of that sighted. So they've actually developed good enough algorithms that they can tell it where to start off on the drive, and then it can recognize hazards ahead of it and figure out its own path forward, heading towards a target. That is, essentially, it interrupts itself when it says, yeah, it's a bad idea. I'm going to go around that, or I'm going to turn a little bit here. And so this is raising the pace of planning a huge amount because you're able to move a lot further and see a lot of different things. Other things that are going on, we've been working with using the Ingenuity helicopter, and by we, I mean not me, to look at the land ahead and help scout out to improve some of this problem as well. That wasn't the major thing that made this fast movement possible, but it is something that's helping enable it more and more as we're getting used to using this tandem system.
Oh yeah, there's no question, right? The future rover, the future combos, you've got the helicopter flying ahead, like laser scanning the entire downrange, and then the rover uses its AI on board to autonomously navigate. That's
the dream.
Yeah, huge distances.
One of the other really cool things is that we missed during the summer hiatus was that Perseverance had a solid detection of salts using the Pixel instrument on the surface. Now, one of the things about salts is they've been pretty elusive. What's showing up on the screen right now is actually a picture from Curiosity a couple of years ago, actually, where we saw these imprints of what looked like salt crystals, but not definitively so on the surface of an outcrop. Wasn't something we could drill to do X-ray diffraction and figure out for sure is it there. There have been a few possible detections through either the SAM-EGA analysis or through X-ray diffraction. Ping me online later if you want to know more about those. But this was the first time where we can actually look at the ground and say for absolutely certain that's salt. And that tells you a lot about the environment that formed this stuff. There was water there. It was a little bit briny. It evaporated. It left this stuff behind. And so that's a huge piece of the puzzle in what was this paleo environment. As far as Curiosity is concerned, we're driving up the side of the mountain. We're getting into some of the steepest terrain we've been in since the beginning of the mission. And we're getting to this, there's a big global change in the geology where we went from stuff that makes clays to stuff that leaves sulfates. And we think that's related to Mars drying out, where if you had a lot of water in a regular cycle, you get kind of normalish lake waters, and that makes clays. But as it dries out, the salts and acids get more and more concentrated, and you end up with highly acidic solutions that form sulfates. And we see this on a global scale. Right now, this is the first time where we're actually driving across that discontinuity, that change from one regime to the other. So really exciting days in the geology ahead for Curiosity, despite like 10 years on the ground now.
Right. Yeah. Yeah. Don't forget about Curiosity. It's still making a lot of amazing discoveries. And we were talking in the pre-show.
Curiosity.
Yeah, yeah, of course. And pre-show, there's some other amazing discoveries coming out too. So maybe save a bunch, and then the next time we talk, we can get another update from you about what's happening. But we're out of time.
Sounds great.
So I want to give each of my co-hosts a chance to shamelessly self-promote what it is they're working on. Nick, you just spoke, so go ahead. What are you working on, and where can people find out more?
Well, oddly enough, the main thing I'm working on right now is a grant proposal that I can't talk about. Sorry, same as last month.
Yeah.
But the thing that people can follow along with, I'm starting to build a road trip with my wife and my infant daughter to go around to national parks across the country and talk science everywhere we go. You can see that at the Wandering Sci. That's wanderingsci.com. Same handle for Twitter and Instagram. I'm not the best about updating that regularly right now, but we're getting there, and our plans are starting to come together. So
Awesome.
Stay tuned. All
right, Dave.
Frequent contributor, Universe Today and Sky and Telescope. And more recently, I've also been writing for Mike Simmons' site Astro Gear Today, doing gear reviews, and also for Vionis Telescopes, giving them just space news articles and what's going on in the sky. And probably speaking of which, the next big astro event, I'll probably write a guide on Universe Today, is there is a very deep partial eclipse, very nearly total on November 19th that we're going to see here from North America. So that ought to be kind of cool. It's like 97% total.
So there will be an umbra.
I think so. I think we'll actually see the moon turn the characteristic red.
Okay,
I heard your remark about how boring partial eclipses were last week.
Last week.
I always watch the show even if I'm not in it, just to make sure you're not talking about
that was kind of directed at you. Were you cringing,
I know it was.
or do you get it?
I got it. Well, you know what I think you're thinking of is penumbrals are the ultimate boring eclipses.
Oh yeah, no. If it doesn't go through the umbra at all, if it's just penumbral, forget it. Not worth.
You barely could.
You wouldn't even notice.
Yeah. Unless you looked at it side by side in a photo, you almost a penumbral you wouldn't notice. But no, so this one's going to be nearly total.
Yeah. So like if we were standing out there and you're like, oh wow, look, a penumbral eclipse, I wouldn't even look. I wouldn't even turn. Awesome. And of course, Astro Guys everywhere.
Yes.
With a Z.
Yes.
All right, Adam, you get a second chance, a bonus chance to shamelessly self-promote. So if people want to find out more about what you're working on, where do they go?
The Space Juggler on Instagram or Facebook.
Fantastic. All right. And I mentioned I've got an interview tomorrow at 11 a.m. with Dr. Mary Wojtek. She is the director of NASA's astrobiology department. So we're going to have a really interesting conversation about sort of communicating astrobiology and the and sort of what role, when do you say what to who, and how do you sort of balance the line between properly communicating science and at the same time trying to contain people's enthusiasm and woo-woo pseudoscience. So it should be a really fascinating conversation. Mostly I'm just going to be getting tips on how to do my job better. So hopefully that'll be good. But that's on my YouTube channel tomorrow. But Universe Today on all the things. Sign up for my newsletter. Listen to the podcast. I'm sure you all know how to find all this stuff. All right. Well, thank you, everybody, for joining me this week. Thanks to all of my co-hosts, special guests. Thanks to all the moderators, especially Nancy Graziano. We couldn't do this without you. Everyone watching on Twitch and YouTube, thank you so much. And we'll see all of you next week. Thanks, everyone. All right. I have no button to press.